All right, I am on page 127. So remember, if you're here, you write down what we do. You're getting the points for it, which is always a bonus. Plus, it'll help you on the last quizzes and tests. All right, and this. You guys all good on a Friday?
Yeah.
Everyone's happy. Plus, we just watched some skate videos, dude. Like,
Not a bad start.
all right. So for 7.2, it says calculate the chi-squared value for the observed value of 4.2, expected value of 3.8. That's the hamburgers. All right, here we go. Y'all ready for this? Here we go. All right, problem number 1. So if we want to find the chi-squared value, remember chi-squared equation, if I remember it off the top of my head, which I don't. All right, here we go. So that's our chi-squared equation, 8. On and off period, yeah. Is that cool? All right, so they gave us the observed value of 4.2. They gave us the expected value of 3.8. So you're going to go 4.2 minus 3.8 quantity squared over 3.8. All right. I shouldn't be the only one that's talking to myself. All right, so this chi-squared value is going to be 0.04. Okay, so it's just basically using the equation, what they plug in. Problem number 2, what does it mean? Y'all open to page 127. What does it mean if chi-squared value is equal to 0? That means your observed and your expected are the same. Okay, that's all it means. Pretty simple. So, friends, if you had a chi-squared thing on a quiz, would you be okay with that? All right. And then it says Ben & Jerry's sales distribution has some of the most popular flavors shown below: half-baked, cherry Garcia, chocolate fudge brownie, cookie dough, fish food, and other. I think we should go over to King Soopers right now and do a selection of Ben & Jerry's ice cream. It then says a random sample of 286 sales at our local supermarkets showed the following raw counts: 32, 35, 28, 26, 16, and 149 other. We wish to know whether our sales at the supermarket differ nationwide. Okay. All right. So first thing I'm going to do is I'm going to actually take that information and I'm going to plug it into Desmos. Can I move off the screen? Everyone good? All right. So Desmos is really, this is where, I mean, Desmos has been a really great tool for us all year, but I think that this is an absolutely fantastic way for you to realize how this tool can actually save you an awful lot of time. So I'm going to change 15% to 0.15. I'm going to change 12% to 0.12, 10% to 0.10. Cookie dough is 0.08, 0.07 for fish food, and 0.48 for other. Okay, so the reason I converted those to a decimal, it's going to be easier to actually do the math that goes with these. So being that we have 286, I'm going to go 32 divided by 286. I'm going to go 35 divided by 286. I'm going to go 28 divided by 286. It's 26 divided by that. $16 divided by 286. And 149 divided by 286. Now let's see. So each of those, I mean, so I could easily convert 0.15 to 15 over 100 or whatever. So that's basically what we're doing. Now I want to do the chi-squared test. Okay, so the chi-squared is going to be the observed and the expected. So the observed is going to be y1 minus my expected, which is x1. We're going to square it. Oops, up here. And divide it by our expected, which is x1. All right, so granted, the graph doesn't really do us that much to look at. I mean, it gives us some pivotal points, but the further away we are, the further we are from our mean. I think I did that observed. Observed would have been observed is y1. Yeah, we got it right. So if I actually were to sum up those values, let's see, I'd actually have to probably use a calculator to do it. So I would be 0.0097 plus 0.123447 plus 0.123444 plus 0.0015 plus 0.593 plus 0.0038. If I were to add those all up, my chi-squared summation comes out to, bless you, roughly 0.61 is a rough estimate. So if I added up that purple column, you just have to do it with a calculator. I don't know how to do it on Desmos right off the bat, so I'm sorry. So that's kind of how the Desmos is going to work with that. So if we were to go and say, what is our null and what is our alternative? So our null hypothesis is, we could say that mu is ice cream flavors or something like that. So we could say that mu is equal to the expected, and then we could say that mu is not equal to the expected. So this basically becomes a two-tailed test. And then create a table showing the observed values. So there's no reason to write down the table, but boom, there's the table of our information. So the very top one is the half-baked, the second one's cherry Garcia, third one fudge brownie, Fourth one is chocolate or cookie dough and fish food, and then other bases on that. So that's kind of where Desmos is going to be helpful for you dealing with these problems. If you move over to page 128, it says a die manufacturer tests to see if their die they may show equal distributions, 1s, 2s, 3s, 4s, 5s, and 6s. They roll a die 1,000 times to test. The raw counts are shown as what they've come up with. Okay, so I'm going to clear this out, create a new table. And what I can do is so I got 158 out of 1,000. I got 170 out of 1,000. I got 164 out of 1,000. I got 154 out of 1,000. I got 178 out of 1,000. And I got 176 out of 1,000. And then our expected values for the actual thing is this should have came out to 1 divided by 6 for each one of these. You have a 1 in 6 probability of any of these showing up. Okay, and then that should do there. And then I can create a new column there. So basically, if I look at my graph, that's basically my expected value at each of the roles. So 1, 2, 3, 4, 5, 6 as we go down. And then I'm going to take a look and say, okay, my observed is x1 minus my expected, which is y1, quantity squared, and then divided by my expected, which was y1. So those purple dots down below kind of signify, let's see, those purple dots down below, come on, darker. Notice they are all pretty much spot on. Each of those values is relatively close to 0 because you have scientific notation for each of those. So I would say that this die rolling company has a pretty good weighted dice. So state the null and the alternative. So number 5, we're going to call mu dice probability is 1/6. So we could say that our null is mu is equal to 1 out of 6, and then the alternative you could say mu is not equal to 1 out of 6. Our table we've already created on Desmos, which is great. Which outcome produces the largest chi-squared value in context? Explain having the largest chi value would mean. Okay, so none of those on that really had the biggest chi-squared. I mean, they were all pretty darn small. But if a chi-square is large, it has the biggest difference between the expected and the observed. So again, if chi-squared 0, that means there's no difference. But if it's really big, then that means something. And then find the total of those chi-squared values. I wouldn't worry about it on that one. I mean, we're talking about a really small probability of any of those outcomes taking place. All right. So that is the homework for this one. So let me put that in because those who are here I figured you did it. Was Laura here?
No, she's busy.
Oh, no. Alex, Connor, Mikey, Kale, Gabby, Lucy. Winter, you're right back there. Reed's over there. Gabby Jones. Weston's there. Kat's not here. Kiker's right there. Jake's there. Ethan's there. Lancaster's not. Larkin back there. Finn is over there. Is Samantha back there? No.
No.
Okay. Austin not here. Maddie's not here. Brad's not here. Bryson's over there. Yulia's there. Daria's there. Chance there. Sophia there. Nathan there. Sweet. All right. So again, friends, if you ever miss when I go over the homework, being I'm not expecting you to do the homework, we just do it in class. Just make sure you watch the video, the first part of the video, copy it down, and show me, and I'm happy to put the points in for you. Is that a deal? It's the least I can do for you seniors as you're moving on out. Okay, I am going to be on 7-3. And as we're going to page 51, would you do me a favor? Go ahead and pull your cell phones or computers out. I mean, I know they're never out. I need you to go to Schoology, and this is where I'm going to show you on Schoology to go. So Schoology for stat analysis, go down to this week, which is like week 15. And what I need you to do is click on the chi-squared test for desmos. Mine will open up right on my thing. You might have to open up a different link. Okay, this is a pretty cool situation which you have access to because now you have it on your phone if you get to Schoology. All right, so in 7.3 it says, excuse me, in previous assignments we created tables which observed expected chi-squared values and were computed. The sum of all the chi-squared values has a measure of the total deviation from the null hypothesis expected values. The larger the sum of the chi-squared values, the stronger the evidence against the null. Okay, hang on. So let's write that down real quick. That's important. Okay, or highlight that. So larger sum of the chi-squared, the stronger the evidence against the null. Okay, so stronger evidence against the null would mean you could reject the null in certain situations. Okay, however, chi-squared values do not follow normal distributions or t-distributions. They follow their own distribution called a chi-squared distribution. Like t-distribution, the chi-squared distribution changes shape somewhat depending upon the degrees of freedom. Several chi-square curves are shown below. So basically, with that thing, if I wanted to show degrees of freedom of 5, that's what that original graph looks like. Mine's a little bit skewed because it's not scaled. And then if my degrees of freedom increases, it's starting to look a little bit more like normal as you go to 15. And this is just a sliding thing that works on your thing. You can change the degrees of freedom. Degrees of freedom 15 is getting to look a lot more like a normal distribution. Okay? So this chi-square distribution is indeed skewed right, but less so as the degrees of freedom increase. So as my degrees of freedom get bigger and bigger, the less and less becomes skew right. Okay? And if let's see if I can make that work. So basically skew right means that tail is moving off to the right. Finding the p-value of a chi-square test is a straightforward process. You calculate the sum of the chi-squared values. So you sum up that column when you use the equation. The sum will be referred to as the chi-squared statistic. Calculate the degrees of freedom. In a chi-squared test, the degrees of freedom are the number of categories minus 1. Okay, so if we had 5 categories, your degrees of freedom would be 4. Okay, it's not the sample size, so don't do the chi-squared. If I was like, hey, we did a random sample of 1,000 people, don't do degrees of freedom being 999. It's the number of categories minus 1. Okay, use the chi-squared on your calculator, which is this, to find the percentage of chi-squares that are farther from the null. The calculator command, don't worry about that because it's right, you have it right here. We'll need to use really large number rather than infinity, but we can use infinity on ours because ours is going to take care of it. So all those things take place. All right. So I'm going to have 2 different graphs that we're going to go with. Okay. So this is our baseball card problem. Remember, you got 40 boxes of cereal that each had a baseball card. And we found that when we opened our 40 boxes, we had gotten this, and we would have expected that we would have gotten 8 of each of those. Okay? So basically, that's our information that we're given so far. The reason there's only 4 dots is we have 2 dots that are the same. We have 7, 8, and 7, 8 twice. Okay? So my chi-squared test will be the observed. So the observed is x1 in our case, minus our expected, which is y1, quantity squared, divided by our expected value, which was y1. Okay? So that is our information that goes along with our thing. So if you look at our chi-squared, we are already given it, but I just wanted to make sure you understand where that comes from. If we go and we sum it up, says the chi-squared measures how unlikely we are to obtain the count for each category if the null is true. The largest chi-squared value above was for card A. This suggests if the null is true, the count we got for card A is the most surprising. The total chi-squared value is the final evidence against the null. In this case, the chi-squared statistic adds up to exactly 2. So if I add up 1.125 and 0.125 and 0.5 and 0.125 and 0.125, if I add all those up, I'm going to get exactly 2. Okay? So this is where that slider thing will work. How many categories do I have listed on this board? How many categories? I have A, B, C, D, E. So categories is 5. So what's my degrees of freedom have to be? Degrees of freedom is 1 less than their.
4.
So we have 4 degrees of freedom. Okay? And then our chi-squared test is 2. Our summation of our chi-squared comes out to 2. So you just bring your slider back to 2. And notice it gives you a p-value of 0.736. Okay? That's the area to the right. Okay? So kind of how a chi-square distribution works is your degrees of freedom cut in 2 becomes the peak, where the peak takes place on your graph. So if I zoomed back in, so our degrees of freedom was 4. So our peak happened exactly at 2. Okay? And that's not coincidental. That happens. That is something that will always take place. Okay? So at some point, the chi-squared value becomes large enough that we can reject the null, which is more into the next section. But more of it's just kind of playing around with this. I think this is a pretty cool thing. I did not come up with this. Somebody developed this on Desmos. I had to go seek it. That's why I put it as a post so you could get to it on Schoology. Okay? So, my friends, what I would like to have you at least take a small look at, if not work on a little bit, is page 129 and 130. Okay? So we will do this on Monday. On Tuesday, we're going to go over the review. And then on Wednesday, we have a quiz, I think I have this quiz, on 7.1 to 7.3. Okay? That's all I have for you. All right, so let me stop.